as I am. Remind you of the contests that are going on. Everyone, if you can, go watch the Lockpick Wizard one because it's lockpicking blindfolded. And there's I think that Hack Fortress just started. And of course, there's Capture the Flag. So even if you're not participating, these are fun to watch. And if you have never participated into a contest before, it's a great way to meet people and to become part of the community if you're new. So I strongly recommend it. Teams are often set up in advance, but they'll frequently take new members, or they just put together spontaneously. Other things, remember that there's a party tonight, and it will be here. And other than that, I'd like to introduce our speaker. This is Ballant. And he got into radios because his grandfather was one of the Lancaster bombers unit in World War II and had an entire collection of these radios, which Ballant was lucky enough to inherit. And apparently he inherited the gene to work with them as well, and he's going to tell us about his latest advances. So please welcome the speaker.
Thank you, Mels. Thank you. Thanks for coming along. Let me just get my slide deck up. That might help. All right. So thanks for coming along today. I wanted to give you a bit of an update on some interesting things that are happening in the radio world, SDR world. Maybe give you a bit of a. Can you hear me all right? Yep. Give you a bit of inspiration for signals that you can explore or tools and techniques that you can use to do your own sort of inquiry, because there are just so many signals out there. It's impossible to cover them all, but hopefully this will inspire you a little bit. So to begin with, does anybody have any ideas what part of the spectrum we're looking at here? We've got a hand in the front row. What do you think? 900 megahertz ISM band is correct. Well done. How did you know that, Skylar?
Well, the 900 megahertz ISM band usually has a lot of stuff in it, and that involves digital modulation, which is usually what you see in the 900 megahertz band.
That's absolutely correct. So there's lots of digital signals there. And it's an incredibly crowded and busy part of the spectrum, just like 2.4 gigahertz. This is down at 900 megahertz, so you get much better propagation, but it's very busy because it's unlicensed. So today we're going to look at the RF spectrum, various parts of it, a bit of an update on aviation and looking above to get signals related to that, doing sort of airborne surveillance, using drones with SDR, and some new signals. So I'll try to do some demos as we go throughout. Hopefully the demo gods are with me. I've got a couple of things here. And the vast majority of the stuff uses GNU Radio. And GNU Radio, can I have a show of hands who's actually used GNU Radio before? Fantastic. And who owns some sort of software-defined radio, RTL, HackRF, USERP, something like that? Nice. Okay. So this is actually the 2.4 gigahertz ISM band. I like to show this one because who can tell me what sort of signals we're actually seeing here? You had your turn, Skylar. Someone else? I'm sure you know. Stand over there. Wi-Fi is one of them. What's another one? That's actually the one I was after. Yeah. The microwave, the humble microwave in the kitchen, when you turn it on, it actually changes frequency slightly. You can see those curved lines there. That's actually the magnetron inside your microwave. So if you're ever in 2.4, and you see something like that, somebody's operating a microwave nearby. And I should also mention that those peaks here, the narrow ones, can anybody guess what that is? Bluetooth is absolutely correct, yes. There are many more channels, but they're all narrow band. And the tool here that's actually running is called Phosphor. It can be used with GNU Radio, and it's a really, really slick way of looking at the radio spectrum. And it accelerates this computation using your GPU. So it's very, very nice. Now, one other thing is, it's always nice to sort of look at a particular part of the radio spectrum. You're restricted to often just the bandwidth of your device, and then also the transport that it uses to connect to the computer. Is it audio issue? Okay. It's not a big deal. So, you know, for example, let's say you take the USRP B200 or B210, that's USB 3. It can do up to just over 50 megahertz worth of instantaneous bandwidth with your computer, but that only gives you 50 megahertz, and there's so much more of the spectrum to actually explore. Wouldn't it be cool if you could actually visualize a much larger portion of the spectrum, maybe not quite in real time, as you would expect with, say, just a single channel, but this here is actually a continuous sort of plot from 50 megahertz to 1.25 gigahertz in GNU Radio. And the way that works is that you can use some trickery of some hardware. It actually uses a networked user like this one here. So this is just hooked up via gigabit Ethernet to my computer. And I might try to... Is that on? Hello? So that is a networked SDR. It's a N210, and it connects to your computer via gigabit Ethernet. And what you can actually do then is ask it for some samples that it will transfer over to you, and then you tell it to switch to another frequency. And you can tell it when to send the samples and when to send the frequency, so you can do this in lockstep. And you can do it so quickly that it will actually, I'm going to try to show you the program actually running now. I don't know how much we'll actually see inside here because what's that? Oh no, I'm going to drag the window across. But of course the demo gods have left me within the space of 2 minutes. Give that one more go. Okay, here we go. So I can't guarantee how much we're actually going to see here because we're inside. Oh yeah, we got something. So if you have a look, this is actually the current spectrum from 50 megahertz to 1.25 gigahertz. 50 megahertz is in the bottom left-hand corner, and then that entire range is sort of cut up into 3 so that you can see them stacked upon one another. So the bottom left is 50, it goes across to the right, then you go through the middle, and then you end up at 1.25 on the right-hand side of the very top one. And on the very lower left, you'll be able to see, if you look really closely, the FM band, and then a whole bunch of other stuff. All the really active stuff there is probably the cellular network, all the different channels there, particularly are in the upper portion of that band that you can see at the top, and some other stuff leaking in. But it's a really cool way just to get a quick sense of a very wide portion of your spectrum. So we said that 915 was really busy. We can actually see that if we play a little video. This is actually running a little bit slower than it would. This is being visualized here using a program called Boardline. Who's used Boardline? Yep. I highly recommend that you check it out if you like to analyze signals both in real time or if you record them and then analyze them offline after the fact. It's a really, really powerful visualization tool and really allows you to drill down and see what's going on. So you can see there's lots of different things going on. A lot of narrow band signals, plus a couple of wider band ones. And then it's interesting because you see things like the mesh networking of smart meters, some new interesting signals pop up that I'll show you in a minute, and rather simple modulation schemes that you could potentially decode and attempt to figure out what it is. If you have a directional antenna, you might go around and try and fox hunt them. So this is sort of zoomed out now. You can see there's lots and lots of bursts all over the place. And a very common sort of scheme that's used to communicate here is called frequency hopping. So one particular radio won't actually always transmit on the one frequency. The entire band might be divided up into, say, 50 channels or 80 channels or something like that. And then every radio will know when to listen at the right time on any particular frequency within this band, and then you'll see sort of signals hopping around. And I'll come back to that and show you how you can actually visualize that to see what the sort of channel occupancy is. So moving along, I just recently switched to Keynote, so I'm just going to add in a gratuitous transition for text every so often. So aviation has always been very close to my heart, and testing 1 2. Can you hear that crackling? Can we have any more volume on this in this mic? Can you hear that crackling? So that's actually the pulses from that radar. This is a primary surveillance radar at an airport, and I've talked about this before, but just to recap, obviously it's sending out pulses, and that will echo off metallic fuselages of aeroplanes, for example, and then you can track them so that the aircraft doesn't have to have any active equipment on board. This is just a little GNU Radio flow graph to receive that. What you can do is you can process that data. You can take an SDR and just hold it up in the air near a radar and record it, and then you can process that so that it synchronizes to the initial pulse of the radar, which is down the very left-hand side there, and then every single time there's a pulse, it records for a while, and that makes up one scan line. So the actual pulse that comes out is on the left, but everything else after the left-hand side is actually energy received from the air, from that pulse reflecting off the nearby environment. Now remember, I was just using an SDR with a whip antenna. Nothing fancy, no directional antenna, nothing like that huge directional antenna that's actually rotating on the radar. But you can actually see that there are these shapes coming out. And if you unwrap that onto the map, this is in the Bay Area, and I put that on the radar, which is near Moffett Field Air Force Base, you can actually see that the bright points actually line up with structures in the bay. So you've got the bridges, you've got the power lines that cross the bay, which form sort of these nice lines. And all the stuff that's really close in is sort of ground clutter. So you can do interesting stuff with primary surveillance radar. Modern aircraft have lots of antennas on there, so there are lots of interesting signals to try to look for. And that, on a 747, there are 31 radios, lots of different things, and that makes someone like me really happy. And then, who's mucked around with Mode S and ADS-B plotting, all that kind of stuff. So you can do cool stuff like receive the broadcast from planes, and is that playing? Yeah. And then actually plot them live on the map as they come to land at San Francisco, and they'll change color when the nose gear touches the tarmac and so on. So just, if you like plane spotting, it's a neat way of visualizing stuff. You've probably seen this. One thing I did a while back was actually implement the system and put it through Google Earth, so you can get this virtual cockpit view as if you were sitting in the pilot seat. So that's actually a plane taking off from SFO, and you can imagine what the view's like, and then it'll swing around to the north, and you can see the city there. I just recently moved up to the city myself from the South Bay, and I set up all my equipment again, so I'm going to try to put it back online and release it all as open source, because it's been sitting there collecting dust. And another interesting part of that whole aviation system is, aside from actually tracking planes, because they will broadcast obviously their position and altitude and other information like that, is ACARS. It's the Aircraft Communication Reporting System. And this operates in the aviation VHF band and is a digital, essentially text messaging for planes for the control systems, or to talk to ATC pilots, to talk to airline ops, the Rolls-Royce engines to report performance data back to Rolls-Royce on the other side of the planet. So there's a global VHF network. And that can be visualized too. So this is the system. I'm originally from Sydney, and I had it set up back there, and every time a balloon pops up, that's actually an ACARS message being sent or received to a particular aircraft. So it spatially shows you what's going on. And it's really interesting because you have lots of messages about the toilets being clogged. This is my favorite old joke. So I added that little Easter egg there for when that's reported. And then also you get waypoints for these long-haul flights, and you can see these ones going to the west coast of Australia, and then those going into Asia there. And that's all good. That uses the terrestrial network, and people have been looking at that. And that's one part of the aviation network. Can anybody take a guess as to what we're actually looking at here? Right. More specifically, though, what this particular angle, this particular perspective, it's in INMARSAT. It's leading into the satellite topic, but this is actually the beam coverage. So this particular satellite, in the data sheet or the public information they give you, shows you the coverage area of their beam, because that satellite's far away and they can hit this entire part of the planet with their coverage. So indeed, we're talking about INMARSAT 3, and it's made up of a fleet actually, and they have a whole bunch in geostationary orbit around the planet to give you quite considerable coverage of the planet with different sorts of beams and services. So I was talking about VHF, but there's also the INMARSAT Iridium constellation, and they also provide services for aircraft. So traditionally, when over land, you might use VHF because you probably have better comms and slightly higher bandwidth. But if you're out over the ocean, for example, you have the option of using SATCOM. There's another one called HF, HFDL, which is pretty cool. That's much lower but in the spectrum, but this is actually nice because it's using satellites. So it uses the L band, and you can uplink and downlink messages and phone calls and so on. And the INMARSAT birds, like many other birds up there, actually are just bent pipe transponders, which means that they will listen and broadcast on one particular frequency with a spot beam to one point on the Earth where they have, for example, INMARSAT's ground stations. And they will also have very wide beams on a different frequency, which are the uplink and downlink for, in this case, the aircraft. And so you can see that how the system sort of works there with the different frequencies where they operate. And what's nice is that the downlink for the aircraft is actually in the 1.5 to 1.6 gigahertz band, which is easily received by software-defined radios. So what do you need? You essentially just need to put a dish up in your backyard. It's a little bit more complicated than that. Because the signal's so far away, you need to filter and amplify. That's to prevent other signals from getting in, and also to amplify that weak signal from the satellite. So you can make this homemade left-hand circular polarized helical feed. This is the handiwork of my good friend Ian Buckley. He just put this together and did some captures for me. He's got this coax running into a bandpass filter, a low noise amplifier, and then another one on the backside, and just hook it up to the SDR. So why is INMARSAT interesting? Well, INMARSAT allows you to exchange messages to and from aircraft, and also set up calls and actually run the call traffic as well. The key to actually looking at that system and the sort of way to open the door is to look at the P channel. There are different channels, but we want to start with the P channel because that's where the coordination and timing begins. It uses TDM, and it carries signaling and user data. You've got the R and T and C channels for reservation information, and then circuit switch mode or random user data from the aircraft. So they're all used at different frequencies, different sort of schemes, but fundamentally you start with the P channel. So that was the flow graph. I cleaned it up a little bit. I don't know if you can tell the difference here. But this is sort of made up of two components. One is the sort of basic signal processing. So if you haven't used GNU Radio before, this is an example of a GNU Radio flow graph. So the raw signal will come in this case in the top left, which is essentially what you see on the dish, and then it will go through a whole bunch of signal processing steps, which I'll explain in a moment, and then it will go through and it plugs into some other blocks in the bottom right hand, and I've written some Python code to actually do the sort of packet parsing and synchronization there. So the first step is that you get this, and you can actually see the spectrum, and you get those little spikes sticking up, and they're actually all the P channels that you can see within this frequency range. So there are actually a couple. And then you click on one, and then you get the green line, and so that's called channel selection. So you pick out the signal of interest, and then you shift your baseband spectrum to that particular frequency, and then you filter, so you get this very narrow band signal that's your P channel that you want to decode. The next step is to determine the modulation type. So what you can do this thing called blind signal analysis, and I've spoken a bit about some tools and techniques that you can use to sort of uncover the layers. The idea is that if there's a signal that you like and you want to sort of discover what's going on, you don't need to necessarily go and research it online to begin with, or have the secret data sheets for it, the specification. You can actually just apply some simple mathematical steps to usually uncover what sort of modulation scheme it is, because it's usually a subset of fairly simple ones. So in this case, it's GMSK, Gaussian minimum shift keying. And what you can do is you can take your signal, square it, take the FFT, which is shown here, and then you should get two of these peaks equidistant from DC. And that's the characteristic signature of GMSK. So we know that the peak channel is GMSK. The next step is you need to know how quickly they're actually sending the information down, which is called the symbol rate. And the symbol rate, or the baud rate, you can determine pretty easily by taking the signal, multiplying it by a delayed version of itself, and then you take the FFT again. And the first big peak you have will actually be the baud rate. So if you read that off, can anybody tell me what the baud rate is? Where's the biggest peak? Frequencies on the x-axis? I hear some S.
600 bits per second.
That's right, 600. We'll call them symbols per second here. So the next step is, once you know what the modulation scheme is, once you know how quickly those symbols are coming down, you then want to begin tracking them and then turn them into bits that you can operate on and then pass into packets. So this step is called clock recovery and is very important. And there are different sorts of algorithms. In GNU Radio, it's just a block that you throw in. And it will actually try to track those symbols and synchronize to it and then sample that stream at exactly the right time so you get that bit, the correct bit out. And you can tell if it's actually working properly, because if you plot the samples, this kind of looks good, right? Because GMSK, the way you can tell is you'll have a whole bunch sort of at one extent at +1 and a whole bunch at -1, and then you're good. If it was looking noisy, then we'd probably be off channel, or the signal might be too weak. If you start actually doing clock recovery on that, then it'll look much the same. But what you can do, this is one nice thing about the visualization tools in GNU Radio, you can switch then to dots view. And these samples, because essentially you're showing data points in between your symbol points, you're going to have dots all over that spectrum, that range, bad choice of words, between -1 and 1. But once you do clock recovery, it's only going to pick basically your symbols that will turn into bits. And you see here, you actually have this nice blank space in between -1 and +1. That means that you've actually synchronized properly and you're sampling bits nicely. But then what you can do is you can slice through the 0 line here and then determine if this is a 1 or a 0. 0 is going to be below, 1 is going to be above, digital 0 and 1. So what you can do then is you can use a raster plot. These are incredibly handy for determining if there's structure within data, because you want to see structure. So I just put those raw 1s and 0s through into the raster plot, and you can see that there's this interesting pattern that forms here. You can play around with the width of your plot and determine that they're 1200 wide frames, and there's this synchronization signature here you can see, because it's the same thing on each scan line. So that's how your decoder will know when to begin decoding the next frame. So once you actually look beyond that, though, it looks pretty random. So generally, especially with satellite links, there's always going to be a combination of interleaving, forward error correction, and scrambling. And there are some very good reasons for that, but that's very, very standard. And it makes good sense when you're making an RF link, especially to space. So here I actually had to go out and search on the internet a little bit, because once you get into forward error correction, and I mean, you can try a whole bunch of stuff, but it just takes a lot of time. So you can cheat a little bit and figure out what the specs are here. And the idea is that you have these signaling units that come down, they're scrambled, they're convolutionally encoded, they're interleaved, and then they're put into that payload after that synchronization thing. And remember how I was telling you that this is the coordination for the rest of the channels? When the frame begins, that's actually when the frames start on all the other channels as well. So therefore, once your receiver synchronizes to this, it'll be synchronized to the rest of the channels too. Those other channels are going to be wider bandwidth to support higher rate stuff like voice. So interleaving is really nice because it protects against burst errors. The way an interleaver works is that you have your raw bit stream, and then imagine this sort of holding cell or this memory. You write in your bits from left to right. And once it fills up, then you actually read it out from top to bottom, and you go across. And what that happens is it temporarily disperses those bits over time, so that if you in fact get a burst error and it corrupts some bits, you can use forward error correction to fix it up, and it won't affect the entire block. It's really quite neat. The next step is doing convolutional encoding. That adds redundancy to your bit stream, so it adds extra bits. And then on the receiver side, you can use, for example, what's called a Viterbi decoder. That will figure out the maximum path through your bits. And if your bits have some errors in it, it will actually figure out which bits are incorrect and then attempt to repair them if they're not too bad. Also a very neat scheme, and it's used all over in the communications world. What's nice is that GNU Radio has many of these blocks already, so it has a convolutional coding block, and you can just throw that down. Interestingly, the code that it uses is the same code, and this has been the most popular code used by the NASA Voyager probe. They used this all the way back then, and it still survives to this day. This has been superseded by much more modern codes like turbo codes that are used in LTE nowadays, but this was still a very popular one. And then descrambling. Descrambling, what it does is it disperses the energy in your signal, so it uses up a lot of your spectrum. And this is just using an additive scrambler. That's sort of an example of how it works. And then there's a block to do that you can just push that through as well. So once you do that, once you put it through all these steps on the decoder side, then you put it back into the raster plot, and you can see that there's a lot more structure in that particular plot there compared to the original one that we had. Also, there's a CRC check, and then you can validate for certain whether you're decoding properly, because then you should get the right CRC. So after all that, then you can start decoding messages. And it took me a little while to figure out, because CRCs can be a pain depending on which bit order you use, and usually it comes out to 0, but certain CRCs come out to a fixed value here. This is F0B8. But what happens is you get these packets coming out. They all start with the first byte that tells you what sort of packet it is, and then you have the payload and a CRC on the end. So I wanted to look for 71, and then the way it works is that it signals that the user data is starting, and it counts down the packets that start with a C or a D until it gets down to 0, and then prints out the message. So it ends when you get to C0. So you get some interesting messages. Now, just to keep this in context, this is why I certainly love this kind of stuff. This is somebody on the ground typed a message into a computer. It was probably sent over the internet to a relay node, and then the ground station. It was turned into radio frequency energy. It was sent up, 38,000 kilometers into the sky onto a satellite. It converted to a different frequency, sent it back down to Earth. This is a satellite that's just sitting there with solar panels, powered off a battery, with some long lifetime. Sent it back down to a plane that's hurtling through the sky over the ocean. I mean, that's pretty incredible. This wasn't about clogged toilets, mind you, but it was telling people to hurry up because late passengers may not be accepted for travel. I hate it when they do that. This was only from a short capture, so I want to take this back and then run it for a long period of time and see what sort of juicy stuff you get. But you got notices here. This airport, I didn't know which one it was, but basically all of their taxiways and runways seem to be closed, which is really helpful. You get weather reports. There are different systems as well, CPDLC, ADSC. You can decode that as well and gain information about where a particular aircraft is heading. And these are aircraft that you wouldn't really have any other contact from. And also what's interesting about INMARSAT is if you put it in the context of tragedies that have occurred in the recent history of aviation, you might remember MH370. If you could listen on the other side of the link, you might do your own Doppler processing and figure out, do some of the clever math they did to determine what portion of the world the last INMARSAT ping was from. And then apparently these aircraft are on time, which is a pleasant surprise. And then you have these weird human-readable messages, advise you have info, no participating T-whip. I don't know what a T-whip is. But I've seen other ones where a plane has been forced to reroute and the federal police are going to be waiting at the airport, stuff like that. So that's INMARSAT, work in progress. But again, just illuminating that there are interesting signals up there as well. So with drones and FTP, next topic. This is actually the 2.4 gigahertz ISM band, which is used to send remote control signals to drones. So it's also very, very busy when you go to like a meetup where lots of people are flying. Make did a little article on this a while back. Who's actually played with a drone or seen a drone flying, and people with the FPV goggles? So people actually now put cameras on their drones and then they wear these goggles so they can see from the point of view of the drone, and then they actually race. I don't know how they do it. They are machines. It is incredible to watch them go and the reflexes that they have, because those drones are tiny and they're so fast. But any ideas what we're looking at here? Any ideas? Anyone take a guess? No.
Video signal coming from over the way?
Video signal is correct. What kind of video signal do you think it is? Not quite Predator, unless he was using ancient kind of technology. NTSC is correct. Who said that? Very good. That's completely correct. So we're looking at a part of the spectrum, and what's weird is that it's not just NTSC, it's NTSC over FM. So you can actually see the vertical sync, the frame sync, and then it actually drawing the picture there. So that's actually how a lot of systems operate, and you get interference, and if people go on the wrong channel, then they'll interfere, and then they won't be able to see anymore, and then they'll crash their two drones, not just one, at least. Drones are fun. They sound, depending on the model you get, they can sound like really big, loud mosquitoes. That's one taking off there. And just as a little bit of a test, I put a webcam on there, and I hooked that up to a USERP E310, which is an embedded USRP. Got one here if you want to have a look. It actually has a software-defined radio plus an dual-core ARM processor inside, plus a whole bunch of other goodies. So you can hook it up with different peripherals, and in this case, because it's small and compact, you can put it on the underside of a drone and then do anything you want up in the air. And as I'm sure you well know, the higher altitude you get, the more signals you see, and often the stronger they are. So instead of going to the top of a building, you can send a drone up into the air. So here, this is a GNU Radio program. The webcam's sending the images to another program. It sends it down over RF. And then this is the screen recording on my laptop. You can see some crazy guy jumping up and down there. My friend's actually flying the drone, so a little bit of fun. I wouldn't recommend that for FPV because latency is very important. There's very bad latency in that system, and it's not terribly robust, but just a bit of fun to prove a point. What's nice, though, and kind of scary is that because you can fly a drone, well, you shouldn't, but anywhere. Has anybody seen that there's an app that I think the FAA put out, and it's supposed to give you advisories on if you shouldn't be flying in a particular area that it determines using geolocation. Friend's fiance showed that to me, and apparently everywhere that she turns it on, it says that you can't fly. But here, you can send them up to quite a high altitude, and you can see into everyone's backyard. I mean, it's quite incredible. So imagine that for RF. So here again, it's taking off, and this is from the point of view of the drone. This is being recorded on my laptop, so it's sending the information down. This was a different system, so sometimes the MPEG stream gets corrupt a little bit, but again, you can very, very quickly go quite high up and just see the landscape as it unfolds. It's kind of neat. One thing you can do on there is run a spectrum scanner, so if you just want to look at the activity in the spectrum, not decode anything in particular, just do a bit of recon. You can run that on there. And as an example, this was the sort of spectrum that was output on the ground. And then up at altitude, those signals were 20 dB higher. So that was pretty nice. And you can just have this run, and it will collect, and then you can come back down, download your results, have a look, and then pick anything that you want to investigate further. That's just the general SDR approach. You can also combine that with other really neat technologies, and because there are USB ports on this thing, you can plug in an Ubertooth dongle. Or you can plug in an Atmel RZ Raven Zigbee dongle, which I happen to have plugged in here. And I mean, that will actually decode Zigbee 2, for example, using GNU Radio. There's a really nice project, GRI EEE 802.11.15.4, that will do Zigbee. And it can run on there as well. But if you want to do other things on there, then you can just plug a dongle in too and use the traditional hardware approach. So Ubertooth has a plugin for Kismet. So I was flying that around a little bit and picked up some Bluetooth packets. And this is something that I've been working on a little bit. If any of you are familiar with Kismet, there's actually a folder there. And correct me if I'm wrong, because hopefully I didn't miss the boat on this. But there was an incomplete Zigbee plugin. And I sort of took a look at it and had quite a lot of nice work done to it. And it would work with this RZ Raven dongle, but it wasn't finished. So I finished it and I sort of hacked it up a little bit because I wanted to get the nice Google Earth plots with the signals and so on. So it kind of treats it like Wi-Fi networks to make that happen. But this is actually now it picking up Zigbee networks. And that's kind of nice. The other thing, and hopefully I can demo that to you in a minute, I'll come back to that. So essentially now you have this airborne platform, and if there are other modern embedded computers as well, if you want to try something else. But this seems to be a good all-in-one package, for example. And then you can do all of these things with your drone and fly them around and hopefully not get into trouble or have the batteries run out. I saw a drone fly away once. It had a firmware bug and it just kept flying. And then it ran out of battery because it was at night and this big blinking thing in the sky. And then it just fell out of the sky. So last night at, I think, 1:40, I decided to order a lift and drive around DC with the Kismet Zigbee thing just to test it out and show you something interesting today. The poor Lyft driver had no idea what was going on. He was very confused because I didn't want to go anywhere. I just wanted to drive around and come back. So it was running there. Actually had, and not only that, but he had all the passenger with all these weird lights and wires all over his car. And I put the GPS antenna mag mount on the roof, and he said, what did you put up there? Are you recording this? So I had the app emote, which is another really nice Zigbee dongle, the Raven, and a B200 Mini, just hanging out the window, just catching the breeze. And so this is the result. I think I ended up picking up over 54, 57 Zigbee networks around. And if you consider, everyone knows about Wi-Fi and Bluetooth, Zigbee is one of those interesting protocols, and it's taking off a little bit, part of the IoT and what have you. And I wasn't expecting there to be so much traffic around, but there are a lot of technologies that use it nowadays. And again, no one's really been looking there, and interestingly now, people are taking more notice and analyzing it in terms of security. So, all the green dots along that green path are networks around this place. I saw some clear text. Something was reporting the time. You could inject packets, and maybe it might be a nice big sign somewhere. You can change the time on there. And then there was this, plain text coming through there. It was just very, very quick analysis of what was there last night. But it's nice because now it's geotagged, and obviously, like with Wi-Fi, can go back. This is the awesome driver, Olatunde. He was a really good sport, especially that late in the night. So what's also nice about this setup is with the E310, you power it off a battery. I've just got it plugged into a USB battery pack, so it's really portable. Just threw it in my bag there, doing its thing. I thought, oh, well, I'm going to catch a plane. I left it running on Wi-Fi. I had a Wi-Fi dongle plugged in. It's down at SFO. That's at Phoenix. I guess the plane was landing or taking off. I don't know. Picking up, in that case, Wi-Fi networks. And then if you dare nowadays, with everything that's been going on, put any sort of antenna up to your window in a window seat, and in this case get a GPS fix, you can see that it's finding the in-flight Wi-Fi. But again, because it's portable and compact like that, you can work on a project in flight. Just just be aware that they will probably do an extra check on your bag. Interestingly, they're far more strict about this in Europe than in America, which is surprising considering everything. I got pulled over like you wouldn't believe over there. So just briefly then finish up some other interesting signals. Z-Wave. Who saw the Z-Wave talk yesterday? Nice. Yeah, it was really impressive. Great tool, home automation. What's interesting is that there are 3 rates that Z-Wave uses. And again, I just wanted to see what Z-Wave was out there. So I put together this flow graph that simultaneously demodulates all of the 3 rates and then just outputs the raw packets at the bottom there. And interestingly, that's sort of the flow graph, bit of a mess. What's new? So I thought, well, if they're doing stuff that we're going to do a demo, I'll take my kit, see if I can pick anything up. And in fact, I was dumping out the frames yesterday. And I actually had it running. That's why I had the B200 Mini there last night in the car. And what's interesting is that Z-Wave is usually quite short range, but at 900 megahertz you get a bit of extra distance. And I actually picked up a whole bunch of Z-Wave driving around too. No geotagging or spatial tagging there, but again, it's just interesting to see that you can get that just by driving around. LoRa is another one. Who's heard of LoRa? Yeah, LoRa's kind of new on the scene. It's part of this whole low-power, wide-area networking phenomenon that's happening in the IoT. Because 2G, GSM, GPRS is going to be sunset and retired, technology needs to replace it, so LoRa is one of the options. Interestingly, it's chirp spread spectrum, which is quite a different sort of signal. And if you look on the left-hand side there, you can see how you see that chirp, the diagonal lines. That's actually the signal, and they encode data in that. So this is a little flow graph that generates and down-converts those chirps so that you can see what the underlying modulation and how the data is encoded there. So if you imagine on the left-hand side in these ones, you see the actual chirp on the raw spectrum, and then on the right-hand side, you have the down-converted chirp. So basically, a chirp is this frequency that increases over time and then goes back. And then in LoRa, it sort of does the chirp, goes the opposite direction, starts going the right direction again, but jumps around in chirp offset. And that's how they modulate data. So if you make your own signal, basically it's just a sawtooth going into a voltage control oscillator, and then multiply the 2 signals, you can straighten those diagonal lines. And that's what's happening on the left. And they claim to have really good coexistence because the band is so busy and there are all these other signals. So with this, you can still get your low-rate signal through. But when you down-convert the chirps, you see how you have that characteristic line of energy? That's actually the LoRa signal. And then at this point, it becomes an MFSK, multi-FSK issue of decoding it. So you just have these spikes of energy that appear all over the place, and depending on what bin of the FFT they're in, that is your data. So it's kind of neat. And what's really cool is in this one, there's actually a BPSK signal going right through the middle of the chirp. And you think, oh, well, the 2 signals are interfering, it won't work. That's what it looks like there. If you down-convert the chirp, that BPSK disappears and you're left with those little bits of energy again. Pretty neat. And I was really confused because I saw these other chirps and I just thought it was LoRa. But there are different sorts of chirp signals out there, and it's not LoRa. I don't know what it is, so if anybody has any ideas, I'm all ears. But it's kind of cool. And that one, again, if you down-convert it, turns out to be the same sort of scenario. So just another interesting signal, sort of new to the scene for you to keep an eye out. Like there's a new mesh network being set up in San Francisco and on the East Coast, various places. Just to finish up then, I wanted to show you how you can sort of, if you're going for a long drive somewhere, you can get a broad overview of the spectrum in one picture really quickly. So I was driving down from, I think, Petaluma back to San Francisco. This is the track. And I had the E310 running there, constantly collecting the 915 megahertz band. It would record about half a second, dump it, and just keep cycling on that. So if you were to pick any one of those individual recordings of half a second, you would see the sort of frequency hopping stuff that we saw before. Or, interestingly, this one, Any wild guesses to what this was? This was just after I finished crossing the Golden Gate Bridge going south. I know you know the answer, Skylar, but anyone else? Yeah, that's right. In this case, it's fast track. So this is the fast track reader as I was going through the toll booth. And what you can do there is that you can take each individual recording, and then for the individual recording, you basically do an FFT of the entire thing, so like a stepped FFT, and then you take the maximum value of all the bins for that entire recording. And that gives you sort of the energy signature of what happened during that time. You take one of those, and then you make that a scan line, a horizontal scan line, and then for each recording, every subsequent recording, that will give you all of the subsequent scan lines in your image. So what you're seeing here is sort of like the heat map over time of the 915 megahertz spectrum. And it's actually a really big image, so when you downsample it, you can't quite make out the detail. But it's interesting to see here on the left-hand side there, you've got this frequency hopping channelized, whatever it is, maybe smart meters, but it's only using the left-hand side of the band. Here you've got a different sort of frequency hopping, wider band channels there, somewhere in San Francisco. Again, you can GPS tag all this as well. And here, this is actually the fast track. I sort of saw this and thought, oh, what's that? And then I had a look at the recording, and then I saw what it was. And then if you're a local oscillator and you get drunk in the 900 SM band, then you get these really terrible signals here. You see how it's diagonal? Shouldn't be diagonal. That's probably an old oscillator warming up. That's no good. And then if any of you have used OP25, it's used by public safety. I've added this new feature where you can enter the encryption key into the decoder, and then it'll pick the right one for whatever network you're using. If you want to do cryptanalysis, you can look at that. I run some cyberspectrum SDR meetups in San Francisco monthly. Check them out. It's good fun. People do cool stuff like hack shock collars for dogs with SDR. And that was just done with GNU Radio and Hack RF. That's it. Thank you very much. So if you want to check out some of this stuff, my personal stuff.